Hello and welcome back to the Honors Topics and Physics unit on forces. So let's say we're looking at a wrecking ball here suspended by a crane, and the wrecking ball is motionless. Are the forces balanced or unbalanced acting on the wrecking ball? Well, if it's stationary and it's remaining stationary, that means that the forces are balanced. Okay, the forces are balanced. So does that mean there's no forces acting on the wrecking ball? Well, there could be no forces or balanced forces. So let's look. Are there any forces acting on the wrecking ball? Okay, well, I'd certainly say that there's a force of gravity going down, and what's preventing the ball from moving down is the cable. So there's a force of gravity on the ball by the earth down, and there's another force of tension on the ball by the cable. So this is the earth pulling the ball down. This is the cable pulling the ball up. Notice that the feeler is the ball in both of these. The second item on your commas should be the same object for everything on your free body diagram. So, and what's the last step that I should do if I want to show that these are equal? Hash marks. Okay. Let's say that we had the wrecking ball and it was moving upwards at a constant speed. Okay, moving upwards at a constant speed. Are the forces balanced or unbalanced? Okay, the forces are still balanced. Okay, the forces on an object are balanced if it's continuing to do whatever it's doing, if it's stationary or moving at a constant speed in a straight line. So in this case, we'll have the force of gravity down and the force of tension up. Okay, what's going to be different about this one than the previous one? Do I still use hash marks to show that the forces cancel out? I do. Okay, this is the exact same force diagram as we dealt before, because balanced forces are stationary, moving upwards at a constant speed, moving downwards at a constant speed. Anything moving at a constant speed in a straight line are the forces of balance. Okay, and here we are moving downwards at a constant speed. It's the same force diagram. We'll just skip that one. Now, what if the ball was moving upwards and was traveling faster and faster? Okay, so if it was moving upwards and accelerating upwards, okay, what do I know? The force is balanced now. No, the forces are not balanced. Okay, what's the direction of the net force if it's moving upwards and going faster and faster? Well, if it's getting faster, that means that the acceleration is in the direction of its motion, which is up, which means I need to have a net force up. Okay, so how should I draw my tension? Should I draw it shorter or longer or the same? My upward tension force. I should draw it longer. Okay. For some reason the force of tension doesn't come up on here, but this would give me a net force in the upward direction. Okay? Alright, wind resistance, we're really just going to consider basically a type of friction, friction exerted by air, and it acts in the direction opposite the motion of an object, typically slows an object down, traveling through it, or tries to slow it down. And we just introduced this one because we're gonna go skydiving next. Woohoo! Okay, so here we've got a skydiver just jumps out of a plane. There's a force of gravity on the diver by the earth. Okay, wind resistance depends on how fast you're going. The faster you're going, the greater the wind resistance. So right when they jump out of the plane, we're going to say they're not moving, so the wind resistance is 0 or negligible. Okay. So what's going to happen is now there's a net force down. Their motion is going to change. They're going to start moving downwards, and they're going to start moving faster. Okay. So now they're moving downwards. There's a force of gravity pulling the skydiver. We've got a little bit of wind resistance, force of friction on the diver by the air. Okay. Now, what's going to happen to their speed now? Okay. Well, the net force is down. Okay, we got a bigger down than an up. They're moving down. That means they're going to speed up. Okay, they're going to speed up. When they speed up, what's going to happen to the wind resistance? The wind resistance is going to increase. Okay. Okay, so now I've got a bigger force of wind resistance pulling them up than pulling them down. Okay. what's going to happen to their speed now? Well, there's still a net force down. Okay, they're traveling down. There's a net force down. They're going to speed up again. Okay. Now, for those of you that are saying, well, we've got a bigger net force up now than we did before. What's different? Well, we're still speeding up. We're just not speeding up as fast. If that makes any sense. The acceleration is decreased, but we're still speeding up. Okay, so what's going to happen to the wind resistance? We're going to go down and we're going to keep moving faster. The wind resistance is going to increase. Okay, now eventually we're going to get faster and faster and faster until we reach a point where the force of gravity down is canceled out by the wind resistance up. Okay, what happens to the motion of the skydiver when the wind resistance equals the force of gravity going down? Does he stop? Or does he move at a constant velocity? Okay. He's not going to stop. You don't just go faster and faster and faster and faster and then stop. Okay, that wouldn't make any sense, would it? You go faster and faster and faster and faster until you reach a maximum speed, in which case you just keep moving at that speed. That's what's known as terminal velocity, and that's the background behind it. When you go so fast that your wind resistance is canceling out your weight, that's terminal velocity. It's not the speed at which is terminal to hit the ground at. It's that. Okay. So now the diver is moving really, really fast, and he's got to slow down. What does he do? Opens up the parachute. Okay. Now, what's going to happen to the force of gravity on the skydiver when he opens up the parachute? Nothing. His weight doesn't change. Okay. What's going to happen to the wind resistance? It's going to go way up. Okay. So now, what's the direction of the net force acting on the skydiver? Up. So if you're moving down and the net force is up, what happens to your speed? Your speed decreases. So he's going to slow down. Strange enough, that's what parachutes do, is they slow you down. Okay. He does not start going upwards. He starts to slow down. All right, last example with some kind of basic free body diagrams. So we're going to go bungee jumping next. We went skydiving. Now we're going to go bungee jumping. Okay, we're going to ignore wind resistance and just kind of look at gravity and the tension of the bungee cord acting on the person. Okay, so person just jumps off the platform. And there's only one force acting on the person. That's the force of gravity pulling the person down. This guy looks like he's having a good time so far. I'd be terrified. Okay, so now he starts to stretch out the cord a little bit. Okay, so he's traveling down, and he gets to the cord and he starts to stretch it out a little bit. Force of gravity's down. There's a tension between the jumper and the bungee cord. What happens to the bungee jumper's speed? Okay, well, he's traveling down. What's the direction of the net force? Down. What happens if you're moving in the direction of the net force pushes you? You speed up. So the bungee jumper continues to speed up. Okay, and in the process, he stretches the bungee cord. Okay, now what happens to the bungee jumper's speed now? Okay, well, what's the direction of the net force? Down. Okay, what's the direction of motion? Down. Okay, what's going to happen to his speed? Speed's going to speed up. Okay, and eventually he stretches the bungee cord until the forces are balanced. Okay, so now the force of tension going up is equal to the force of gravity going down. What happens to the bungee jumper's speed? Does he stop? No. He keeps moving at a constant velocity. Okay? So he just stretched out the bungee cord to where the forces are balanced. At that exact moment that the forces are balanced, he travels at a constant speed. Okay? But since he's still stretching the bungee cord, he stretches the bungee cord, so now the force of tension on the bungee jumper is greater than the force of gravity. This is finally when the net force is acting up on the bungee jumper, okay, and motion is down. He's going to start to slow down. That's the first part. Okay, so work on free body diagram worksheet 4-2, and that's it for today.